Welcome to 2.1 More on Derivatives. On this lesson, we're going to be talking more about derivatives and differentiability. So recall that a differentiable function needs to be smooth and continuous. So if you have a function that's not smooth or continuous, we say that it's not differentiable at those points. So first example, list all the x values for which the function appears to be not continuous and not differentiable. Okay, so let's go ahead and list all the values. So I'm going to go ahead and mark an A on the x values that are not continuous. So if I follow the graph, recall that a continuous function is a function that you can draw without lifting up your pen or your pencil. And it seems like right here at this x value, 6 is discontinuous, which means not differentiable. Anytime that you have a function that's not continuous, at a certain point, automatically, that point is not differentiable. So here's one thing to add to your notes. Differentiability always implies continuity. If a function is differentiable, then it must be continuous. Now, the other way around is not true. A continuous function does not imply differentiability. For example, let's take a look at this piece of the function right here. That function is continuous everywhere from 1 through 6, but here at this point and here at this point, it's not differentiable because, first of all, it's not smooth. Notice that there's a sharp point. In the last lesson, we discussed about sharp points. Sharp points are not differentiable. Neither are vertical tangents. If you notice, that's a vertical tangent line going through that graph. So let's go ahead and continue this lesson. So I think only x equals 6 is the only non-continuous point of this graph. Okay, now let's go ahead and take a look at differentiability. So I'm gonna go ahead and do this in blue. I'm gonna mark a B for every x value that the function is not differentiable. So it appears to be at x equals 3, where the function is not differentiable because of the sharp point. Also, x is equal to 4 because of the vertical tangent. And because the function is not continuous, automatically it fails differentiability. And x equals 8. So it appears that only at x equals 6 the function is not continuous, but at x equals 3, 4, 6, and 8 the function fails to be differentiable. Okay, in other words, the derivative fails to exist, and we all know what derivative is. The derivative is slope. In other words, if I look at x equals 3, I notice that the slope is a negative slope from the left, and then a slope from the right is also negative in the other, and it's positive, but there is no smoothness to how the slope transitions from one side of x equals 3 to the other side. In other words, what would you say the slope at x equals 3 was? You can't answer that because you don't know. Same goes for x equals 8. If I look at the slope from the left, I got pure negative slopes, but the slope from the right are positive slopes. What is the slope at exactly x equals 8? Well, at x equals 8, it's a vertical tangent. And we know that vertical tangent, the slopes of vertical lines, are undefined. So it's not defined, which means the slope is not defined, the derivative does not exist. Example number 2. Here we're given a graph, and we have to find these 3 characteristics of the graph. So it says here, at which labeled points is the slope of the graph 0? So we're talking about points. We're talking about slopes at the point, not the actual point itself. So let me go ahead and just try to make a visual representation of each slope at each letter. So here is A. A is a negative slope, B is a horizontal slope, which is 0. C is a positive slope. D seems to be also positive. And E is positive. I'm sorry, no, not positive. E is 0. And F is negative. Okay, so which are these slopes that are 0? Well, it's the points B and E. Which are the slopes that are positive, in other words going up from left to right? It's C and D. And last one is this, the negative slopes are A and F. Okay. Remember that a slope of a tangent line is when the graph touches when the line touches the graph at that one point, but just barely touching it. Let's go to the next one. Example number 3. Let f be a function which satisfies this this relation here for all real numbers h. Find f prime of 2. Okay, now let's backtrack. First of all, that little prime in here, we all know what that means. It means a derivative. Well, what is the derivative definition? The derivative definition is the limit as h approaches 0 of the secant equation, the secant line equation. Now, we're going to use this fact. We're going to use this fact here so that we can try to solve this derivative at f prime of 2. What are we trying to solve? We're trying to solve the derivative at x equals 2. We don't know what that is yet. Well, if you notice that this part looks a lot like this part right here. What are we missing from this box that this box has below it? We're missing a divide by h. So let me go ahead and rewrite this. F of 2 plus h minus f of 2 is equal to 5h minus 3h squared plus 9h cubed. If I divide both sides by 2, I have a very similar equation that I'm highlighting right here. Very, very similar. Now, what is this highlighted part missing that this formula has? Well, it's missing the limit. And the limit tells me that if I'm taking the limit of this equation, then I'm taking the derivative of something. So let me go ahead and add limit to both sides of these equations. So I'm going to put here the limit as h approaches 0, and over here I'm going to try and squeeze in here the limit as h approaches 0. Okay, so what does this mean? This means that this whole part right here represents f prime of 2, because notice that in my derivative equation I have x and I have x, but over here I have 2's and 2's, so that means I'm taking the derivative at x equals 2. Okay, let me go ahead and proceed. So all of this mess equals f prime of 2. Now I have the limit as h approaches 0 of 5h minus 3h squared plus 9h cubed, and I notice that I have an h below, so I can cross out an h here, 1 here, and take 1 away from the cube. That one goes away, and now I have the limit as h approaches 0 of 5 minus 3h plus 9h squared. Applying the limit into my h's will result 5 as the answer. So my f prime of 2, my derivative at x equals 2, is a positive 5.